Our next speaker, is Mike Hermele. Okay, Mike.
Great. Okay. Can everyone hear me all right?
Yeah.
Good. Okay. So yeah, thanks everyone for coming to my talk. So I want to tell you about subsystem symmetry fractionalization on point-like excitations. And this is something both quite new and quite simple. So maybe it's perfect for a 15-minute talk. And this is work in progress with Arpit Dua, Jose Garre Rubio, David Stephen, and Dominic Williamson. At least some of them are here in the audience. And we're still exploring various implications of this. So this is definitely work in progress. Okay, so let me start with some motivation. So there's a general question, which I think is pretty familiar, which is how are topologically ordered phases enriched in the presence of some symmetry? And you could ask this question for fracton ordered phases, but really I have in mind just ordinary topologically ordered phases, like phases with anyons in 2D with a TQFT description. And a lot is understood about this question when the symmetries are internal symmetries, just ordinary internal symmetries. I don't think it's fully understood, but we know a lot. But a much more open question is to ask, well, what about if we have subsystem symmetries? Okay, and so this is something that my collaborators actually studied in some recent work, not with me, but before I got involved in thinking about this. And one thing that they came up with is an elegant no-go argument, which seems to contradict the title of this talk. So I better explain it. Okay, and so the picture, so if you look at these pictures, imagine that we have a linear subsystem symmetry S, which acts on this blue line, and we have a state with two mobile point particles. Let's imagine we're in 2D and this is an anion A and some anti-anion A bar. Okay, and the subsystem symmetry S can act on this state, okay? And if you just looked at this picture, you might say, well, maybe A could carry some fractional charge of the subsystem symmetry S or something like that, okay? That's pretty familiar sort of thing. However, because A and A bar are mobile excitations by assumption, we could consider another state where A bar has moved off this line, and then the subsystem symmetry no longer acts on A bar. And in fact, all of the action of the subsystem symmetry on this state is the action of the subsystem symmetry on A itself. And so it follows from this argument that the A excitation has to transform as if it's a locally creatable excitation under the subsystem symmetry S. And actually the same argument applies for any transformation property having to do with not just one generator of a linear subsystem symmetry, but any finite number of generators of a linear subsystem symmetry. Okay, so the conclusion that you might draw is that subsystem symmetry cannot be fractionalized on mobile point-like excitations. And as a consequence of that potential conclusion. So, most of what's in this previous work of my collaborators is not thinking about this, but actually going on to studying subsystem symmetry fractionalization on loop excitations of three-dimensional topological orders. Okay, but this talk is about a way around this argument. And just to be clear, this conclusion of the argument is completely correct. Okay, I think the argument is a correct argument for this conclusion, but there are more subtle kinds of subsystem symmetry fractionalization that are possible, as we'll see in a second. And so this conclusion is not quite right. There's actually a way around it. Okay, so I'll explain this just by telling you about a concrete example. Okay, so the rest of the talk is going to be about this model. It's a very simple model. We work on the 2D square lattice, and we put one qubit on every edge, and we also put a qubit on every site, okay? And the Hamiltonian's a sum of commuting terms, so this is just a stabilizer Hamiltonian, okay? There are two kinds of AV terms, which are products of Z operators, and so AVX is a product of these three Z's, two on edges and one on a central vertex. AVY is the same, but it's oriented vertically. And BP is like a plaquette term of the toric code model, but it's decorated with these X operators on the corners. Okay, and one thing to observe is if you take a product of the two different AV operators on the same vertex, you actually get the standard vertex operator, star operator of the toric code model. Okay. I think it's not that surprising if you stare at this Hamiltonian for a little bit that it can be disentangled by a local unitary to the standard Z2 toric code and a trivial system. The trivial system is just a bunch of decoupled qubits in a Zeeman field. Okay, so this model really has toric code topological order. If you don't care about symmetry, that's really all there is to say about it. But this model also is invariant under a subsystem symmetry, and that's what I want to think about. So this is a Z2 symmetry, and it's a linear subsystem symmetry. It acts on rows and columns, and it only involves the vertex qubits. Okay, so you can take a product of z's along a row, only on the vertices, or a product of z's along a column, only on the vertices, and you can check that these commute with the Hamiltonian. Okay, so we want to think about this, this symmetry. And the first thing to do is just ask what kind of excitations does this model have, and how do they fit into the structure of the toric code topological order. So there are BP equals -1 excitations, okay, and these are just M particles. Okay, there's nothing, we're not going to say anything else about them because the symmetry doesn't have any interesting action on them. And more interesting are going to be the E particles. And so it turns out that the E particles they live at vertices where we excite these AV terms. And you get an E particle when one of the two AVs is -1, but the other one is +1. And you can do that two ways. So there are two flavors of E particles, which I'm going to call EX and EY, depending on which vertex term is excited. Okay, and finally, you can fuse these two E particles together and you get a local excitation where you flip both vertex terms at a given vertex. So this is a local excitation. It's created by the X operator at the vertex. And this is a local excitation, but it's charged under the symmetry. And it carries a single non-zero row charge and a single non-zero column charge under the subsystem symmetry. All right, so those are the excitations. Now, it turns out a very simple thing to observe, you'd see it just by playing around with the model, that the E particle excitations are actually symmetry enforced line-ons. So if you think about dynamics of this model that respects the subsystem symmetry, an EX particle can move along a row just fine, but if you want it to turn a corner and start moving along a column, you can't do that with symmetry preserving dynamics. And in fact, for this EX to turn a corner, it can do that, but what you have to do is you actually have to insert one of these local excitations, which is charged under the symmetry at the corner. Then that actually turns the EX into an EY, and then it can move along on its way in the vertical direction. Okay, so if we enforce the subsystem symmetry, these E particles actually behave like line-ons. All right. Okay, so here are some other just kind of general things we can say about excitations before we get back to the E particles again. So given any excitation, we can define some quantities that I'll call row and column indices that'll turn out to be quite important. So let R be the number of non-zero row charges. You just add up how many row charges, could be 0 or 1 because it's a Z2 symmetry. So you just count how many you have, and then you take that modulo 2. And C is the same thing, but it's for the number of non-zero column charges, mod 2. So as an example, if you take one of these local excitations where you flip two vertex terms at a given site, for this excitation, R and C are equal, and they're both equal to 1. Okay, because this excitation has only a single non-zero row charge and a single non-zero column charge. And it's a fact, which is not hard to establish, that actually for any locally creatable excitation, either R equals C equals 1 or R equals C equals 0. So these row and column indices are always equal for locally creatable excitations. Okay, and another kind of observation to make about R and C is that, you know, in order to compute them, you actually have to think about all the subsystem symmetry generators. And if you're working in an infinite system, there are an infinite number of those generators. So if you have some kind of symmetry action that has to do with these indices R and C in a fundamental way, it might be able to get around this argument, because I said this no-go argument it applies when you look at symmetry transformations involving a finite number of the subsystem symmetry generators. Okay, and so indeed, it's possible to understand in a variety of different ways that the e-particle excitations in this model really do enjoy a kind of symmetry fractionalization of the subsystem symmetry. It's not just that they have this interesting symmetry restricted dynamics, but that really is tied to, it's fundamentally tied to something that you really need to think about as a kind of symmetry fractionalization. So I'm not going to go through the details of all of the arguments for this, but let me just tell you the kind of some of the bottom line conclusions. So the simplest way to think about this is that, these E excitations, you should be able to assign them some charges under the subsystem symmetry. And the claim is that EX excitation carries only a single row charge and it doesn't carry any column charges. And of course, that's consistent with it being able to move in a row, but not being able to change its direction and move vertically, preserving the symmetry. And for EY, it's the same, but EY carries a single column charge and it doesn't carry any other charges. So this is consistent with the mobility of the EX and EY excitations. And it's possible to argue for these charge assignments in various ways. And one important thing to observe is that these assignments are not possible for locally creatable excitations because, for example, this E particle has R equals 1 and C equals 0. So such assignments are not possible for locally creatable excitations. One thing that it's possible to give a very simple argument for is you could say, if you wanted to be a devil's advocate and say like, well, maybe there's something wrong with these charge assignments, you could ask, is it possible to assign subsystem symmetry charges to the E particles that would be consistent for local excitations? And you can give a very simple argument that that's not possible. That's not consistent with their mobility and in this model. Okay. Now, another thing you might wonder about this is this really some kind of symmetry fractionalization? So it is. And the way that I think about this is that one of the most basic properties of non-trivial symmetry fractionalization is that if you have a single particle on which a symmetry is fractionalized, there's no way to neutralize that particle under the symmetry by binding local excitations. So imagine a spin-a-half spin-on. You can never neutralize its spin by binding spin-1, spin flip excitations. Okay, so here it's possible to show that there's no way to neutralize one of these E particles by binding locally creatable excitations. And so this really is a kind of symmetry fractionalization. All right, but there really is something subtle about it. And here I get to things that we do not completely understand yet. So these are just, somehow this slide got shifted a little bit, but that's okay. So these are just some comments more about what we don't quite understand yet. So there's a familiar mathematical framework for symmetry fractionalization. This is a piece of it anyway. So usually we would characterize symmetry fractionalization by an element of some second cohomology group where G is the symmetry group and A is the fusion group of abelian anyons. And this has to do more specifically if you have symmetry fractionalization on an E particle with the idea that there are some operators that give the localized action of symmetry on that E particle. And if you multiply them, they don't have to form a representation of the group, but there could be some phase factor, which will be plus or minus 1 valued. And it's a cocycle in the language of group cohomology. And so if you just naively apply this formalism here, where you take G to be the abstract group that's generated by all the subsystem symmetry generators, and you take A to be Z2 if you're just looking at E particles, you actually conclude that the cocycle corresponding to symmetry fractionalization that I just told you about is trivial in cohomology. And it comes from the fact that you can redefine these operators, these symmetry localized operators. These redefinitions really, they're changes of relative phase between trivial and non-trivial superselection sectors. And if you look at these pictures, the picture on the left is a state in the trivial sector. The picture on the right is a state in the E sector. The action of a subsystem symmetry on certain rows in those two states is exactly the same in the two sectors. And so it's actually very unnatural to allow for these redefinitions. And so what this is telling us is that this framework, or at least this very naive application of this framework to this example, is really not appropriate. And so there's something interesting here. It's a little different from ordinary symmetry fractionalization. Okay, so that's the end of my time. So I'll just sort of say what the outlook is, things that we're still in the process of currently exploring. It's good to try to come up with examples with other symmetries or other underlying topological orders. And of course, you know, this is just one example that I told you about. We might wonder what we can say about this kind of phenomenon more generally. All right, thank you.